So 3.6, prove theorems about perpendicular lines, and we're looking at page 182 in your textbook. Let's walk through the notes, and then we will look at all the examples in the book here in just a minute. So 3.6, prove theorems about perpendicular lines. Our objective is I can find, that's our main verb, find. What is it we want to find? I want to find the distance. And what distance is that? It's the distance between a point and a line. So our essential question is, how do I find the distance between a point and a line? So what we're talking about here, for example, is a line, and then there's a point that we are given, and we have to figure out the distance from that point to the line. Of course, we could find the distance over here, but what we want is the shortest distance from the point to the line. And so our first statement is that the distance from a point to a line is the length of the perpendicular. So that's the shortest distance, is the length of the perpendicular segment from the point to a line. So if you would emphasize on your notes that we're starting out with a line and a point, and then we want to find the perpendicular distance, would be another way of saying it, the perpendicular distance from A to the line. If two lines intersect, and these are different theorems that will help us to be able to determine what that perpendicular distance is. If two lines intersect to form a linear pair of congruent angles, linear pair, so put them together, adjacent angles that create a line, and they are congruent angles. So what we're talking about here is here's two lines put together creates a line, or two angles put together creates a line, so they're a linear pair. And these two angles also, they tell us, are congruent. So angle 1 is congruent to angle 2. Then the lines are perpendicular. They're saying that this line, the vertical line, would be perpendicular to your horizontal line. So again, linear pairs that are congruent are going to be creating perpendicular lines, and therefore this angle would be a right angle, 90 degrees. To say the same thing with symbols, we'd say angle 1 is congruent to angle 2, as you see, and then therefore that symbol there with the 3 dots can be used in different professions. For example, math uses it to say therefore. Just a simple, easy way to, instead of writing out the word, you just put the 3 dots. Therefore, the measure of angle 1 equals the measure of angle 2, which, in order for them to be a linear pair, both of them have to be 90 degrees. If two lines are perpendicular, so here's my two lines that are perpendicular, then they intersect to form 4 right angles. And you've seen it before where you have two intersecting lines and only one of the angles is identified as a right angle, and of course you know that all the rest of them also have to be 90 degree angles. Because let's take it one at a time. So here's a linear pair. If this one is a right angle, in order for these to be supplementary, this other angle over here would have to be a right angle, and therefore you can also do the same thing with angles 1 and 3. If two sides of two adjacent acute angles, so two sides of two adjacent acute angles, acute of course means less than 90, adjacent, let's remind ourselves that the definition for adjacent angles means it's a common vertex. So here's your common vertex of these two adjacent angles, and also they have a common ray. So here's your common ray between these two adjacent angles. So if two sides of two adjacent angles, acute angles, are perpendicular, so now they're saying this side of the adjacent angle and this side of the other angle that's adjacent, these guys are perpendicular, so in other words they form a 90 degree angle together. Then the angles are complementary. Seems kind of obvious, but just want to make sure it's lay it out there clear to us. So if the measure of angle 1 plus the measure of angle 2 equals 90 degrees, then of course that they are complementary. Perpendicular transversal theorem. It's saying that if we have a transversal, here's your transversal that cuts across these other two lines, and that transversal is perpendicular to one line that is parallel to another line, then that transversal is also perpendicular to the other line. So in the black is what's given to us. You can think of it that way, that we are given that these two lines are parallel and that we have a transversal that cuts across one of the parallel lines at a 90-degree angle. So now we know that this top line is perpendicular to the transversal. Because the lower line is parallel to the top line, therefore this transversal is also going to be perpendicular to your second parallel line. So to write that in symbols, we'd say that J is perpendicular to H, your transversal is perpendicular to H, and H is parallel to K. Then, or therefore, J, your transversal, is going to be perpendicular to K. Lines perpendicular to a transversal theorem. So in a plane, if two lines are perpendicular to the same line, so here's your same line, and here are your two lines that are both perpendicular to that same line, then they are parallel to each other. Then we can say that these two lines are parallel. So again, what's in the black is what's given to us, and what's in the red is what we are able to determine based on what is given to us. And in symbols, you could say that line M, of course, is perpendicular to line P. So this line is perpendicular to the transversal, and line N is perpendicular to line P. Therefore, M is parallel to N. Let's look at the book now on page 183. Page 183, example number 1, and kind of walk through these. In the diagram at right, line AB, here's line AB, is perpendicular to line BC. So these two lines are perpendicular to each other. If we had the slopes, of course, just to remind you that the slopes would be the opposite reciprocal of each other. But in this case, this slope is a vertical line that's undefined, and this is a horizontal line. This has a slope of 0. But of course, 0 over, you could, with 0, a slope of 0, you put a 1 underneath it, and then if you were to take the opposite reciprocal, you'd flip it over, so you'd have 1 over 0, which is the same thing as saying undefined. That's if we had the slopes, but here they're just telling us, I just wanted to include that as review, but here they're telling us that these two lines are perpendicular to each other. So what can you conclude about angles 1 and 2? Well, because they are perpendicular to each other, it means that they intersect at 90-degree angles. So this is a right angle here, and if 2 is a right angle, then 1's also going to be a right angle, and therefore 1 and 2 are going to be supplementary to each other. And of course, these angles down here would also be right angles. All 4 of them would be right angles. Example number 2, prove that if two sides of two adjacent acute angles are perpendicular, so they're telling us that DE and EF are perpendicular to each other, then the angles are complementary. We want to prove that they are complementary. So we are given, like I just said, that ray ED, remember to review that E is going to be your endpoint, and it starts at E and then goes through D. So ray starts at E and goes through D, and that's perpendicular to ray EF, starts at E and goes through F. And so if these two guys are perpendicular, as is given, this is a 2-column proof here, statements on the left and reasons on the right, then we can say that angle DEF, remember the center letter here is your vertex, so DEF is a right angle, and we know that because perpendicular lines intersect to form 4 right angles. And because this is a right angle, we can also say that the measure of angle DEF is 90 degrees. That's the definition of a right angle. Then we can also say that the measure of angle 7 plus the measure of angle 8 equals the entire angle. The 2 parts equal the whole. Remember, that's the angle addition postulate. And then we can say that the measure of angle 7 plus the measure of angle 8 equals 90. Now, how can we say that? Well, look back here and notice that this second statement is the same, or I guess the fifth statement is the same as the fourth, except for the very end. And we had said that the measure of angle DEF equals 90. So what we're doing is we're substituting. We're taking out the measure of angle DEF and we're substituting in 90 degrees. So that's the substitution property of equality. And therefore, since the measure of angle 7 plus the measure of angle 8 equals 90 degrees, therefore 7 and 8 are complementary, because that's the definition of complementary. So please, you might want to even back up and review that, or play that video, this portion of it again, just to get the thinking of the logical, rational thinking of building a proof. It takes practice to be able to do that. To recognize the right answer as I walk through it is important, but that's not all. You also have to be able to create the reasons and the statements at times. So please do practice that. Next page, page 184, over on, for example 3. So determine which lines, if any, must be parallel in this diagram and explain your reasoning. So we're given that line P is perpendicular to line S, and also line Q is perpendicular to line S. So what can we say? What can we say about lines P and Q? Because they're both perpendicular to line S, therefore lines P and Q are parallel to each other. So I'm just ignoring lines T and U for right now, and just looking at how these two lines, P and Q, both intersect this transversal of S at a 90-degree angle. Therefore, lines P and Q are parallel to each other. Then you could do the same thing with these two lines, S and T. So let's ignore line U and just look at, and also line P, and just look at lines S and T, and notice how both of those are perpendicular to the same transversal of line Q. And so therefore lines S and T are parallel with each other. And I think that's all that you can say. Yeah, just those two. All right, example number 4. Now, do pay attention to this. In previous sections, the last examples were not as important. They were kind of beyond what was really necessary, but at times it does that. But for this example, really is important. It's really introducing another concept that's essential to be able to satisfy this objective if I can find the distance between a point and a line. So here's a sculpture, funky looking sculpture, and here's a diagram of that sculpture, and they're asking what is the approximate length of segment SR. So here is segment SR, and what is the approximate length of that? And of course that's pretty simple. But what they're actually really saying is, if there was a line that went through PR, what would be the distance from S, point S, to line PR? And in order to ensure that this distance between S and R is the perpendicular distance, we need to find the slopes. We need to find the slopes of both of these lines to confirm that the slopes, the product of the slopes is -1, or another way of saying it, the slopes are the opposite reciprocals of each other. So again, assume that there's a line going through PR, and what is the distance from point S to line PR? And it has to be a perpendicular distance. So let's find the slope. That's what they did here. We've done this before, so I'll just kind of breeze over it. The slope of PR would be, you'd call this point 1 and this point 2. And then remember the slope formula, y1 or y2 minus y1 over x2 minus x1. Plug those numbers in, and you'd have a slope of 3/2. Now, does that make sense? A slope of 3/2. First of all, it's a positive slope. Does that make sense that this line here is positive? Yep, because if you were to sign your name, you'd go left to right, you'd go up, and so that's a positive slope. Now let's find the slope of line SR. Line SR. And do the same thing same idea that we just did, and you'd find a slope of -2/3. Now, does that make sense? That the slope of this line here going through SR is negative? And yep, that does, because if you were to sign your name, you'd going down, so that's a negative slope. All right, so now I have the slope of those two little segments, and now the question is, are those two segments perpendicular to each other? Well, let's start out with this one. 3/2, what is the opposite reciprocal of 3/2? You go positive to negative, and the reciprocal, you go from 3/2 to 2/3. Yep, so these guys are the opposite reciprocal of each other, which means that these two segments are perpendicular to each other. Another way of confirming that would be to remember the product of two slopes that are perpendicular to each other is -1. So let me get a sheet of paper here. Let's take 3/2 and multiply it times -2/3. And if we were, positive times a negative is negative, and the 3's would cancel out and the 2's would cancel out, and we'd be left with -1. So yes, these two slopes are perpendicular. So because this is the perpendicular distance from the point to this line, therefore we can find the distance. And now we need to dredge up the distance formula, and I wish they would have written it out here. I don't like the way they just kind of give it with numbers already plugged in. So remember to write out the distance formula. Distance equals, let's see if I can remember it, x2 minus x1 squared plus y2 minus y1 squared. So we need to remember how to do that distance formula. Also, because of the cumulative test we have coming up, covers all of chapters 1 and 2 and 3, and so remind yourself of the distance formula, and that's what they've done here using these 2 points. Just plugging in these 2 points into the distance formula, and they got an answer of approximately 18 inches. And I think that's it. Yep.